Now in this lecture we'll find out the length of chord BC. In the drawing we have a semicircle. Know that the center of this semicircle is at point O. Inside this semicircle we have square DEFO, and we know that the area of this square equals to 5 square units. Our mission is to find out the length of this chord called CB or BC. Okay. So first of all, because of the fact that DEFO is a square, we know that all the angles inside any square are right angles. Therefore, those 4 angles, they are all right angles. So we can write it down that this angle equals to 90 degrees. This angle it is also equals to 90 degrees. This angle equals to 90 degrees, and finally this angle it is also equals to 90 degrees. So we actually know that the area of this square DEFO equals to 5 square units. Here the 2 squared brackets is the sign for the area, so it means that the area of square DEFO equals to 5 square units. We note that the area of any square equals to one side of the square squared, or side times side is equals to the area of any square, and the area of our square DEFO equals to 5 units. So 5 equals to side times side of our square. That is to say 5 equals to the side of square DEFO squared. We take a root out of this equation and we found out that one side of square DEFO equals to the square root of 5 units. That is to say, all the sides of square DEFO equals to 5 units. EO equals to the square root of 5 units, FO equals to the square root of 5 units, DE also equals to the square root of 5 units, and finally DF also equals to the square root of 5 units. In the next step we will join points D and O together by straight line. By joining points D and O, we created here the right green triangle, triangle DFO. This green right triangle DFO. Again, this angle DFO equals to 90 degrees, therefore the green triangle is the right triangle. Therefore we can implement the Pythagoras theorem on the green right triangle DFO. So I'll copy the right green triangle in a new page and we'll implement the Pythagoras theorem in this triangle DFO. We already found out that DF equals to the square root of 5 units, FO equals to the square root of 5 units. The only missing side is DO, that is the hypotenuse of triangle, the right triangle DFO. So we'll implement the Pythagoras theorem on the right triangle DFO. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this right triangle, DFO, the hypotenuse is DO, therefore the square of the hypotenuse is DO square. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DF square plus FO square. So DO square, this is the square of the hypotenuse, equals to df square. df equals to the square root of 5, therefore df square equals to the square root of 5 square plus fo square. Fo also equals to the square root of 5, therefore fo square equals to the square root of 5 square. So in conclusion, we found out that do square equals to the square root of 5 square plus square root of 5 square. Square root of 5 square equals to 5, so it is 5 plus 5. So we found out that do square equals to 5 plus 5, that is 10. We take out of this equation and we found out that DO equals to the square root of 10 units. The hypotenuse, the length of the hypotenuse equals to the square root of 10 units. So we can write here that DO, the hypotenuse equals to square root of 10 units in its length. But what is exactly line segment DO? It starts from the center of the semicircle, that is to say from point O, and ends at point D, that is the point of the semicircle itself. This is exactly the definition of a radius. This is to say, DO is the radius of the semicircle that is equals to the square root of 10 units. Point O is the center of the semicircle. Point B is the point of the semicircle itself, therefore OB is the radius of the semicircle, that is to say, it is equals to square root of 10 units. Likewise, point O is the center of the semicircle, point A is the point of the semicircle itself. Therefore, OA is the radius of the semicircle, that is equals to square root of 10 units. In the next step, we will implement the Pythagoras theorem. Before that, I will present to you a new rule, rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. I write it down. The sum of the angles on one side of a straight line is equal to 180 degrees. So if we have here, if AB, this line segment AB is a straight line, and we have this point K on the straight line AB, and we have here KL. So if we focus on the upper side of the straight line AB at point K, here the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. That is to say, this angle plus this angle in total, they must be equal to 180 degrees. This angle equals to, it is actually angle AKL plus this angle equals to, it is actually angle LKB. So in total, the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. So it is the sum of the angles on the upper side of the straight line AB that is equal to 180 degrees. Likewise, the sum of the angles in the lower side of the straight line AB must be equal also to 180 degrees. That is to say, this angle equals also to 180 degrees according to this rule, rule number 1. We actually can implement rule number 1 in our drawing. Why? Because in our drawing we have this semicircle. This is a semicircle, and we know that AB is the diameter of this semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. AB is a straight line. So if you focus on the upper side of the straight line AB at point O, the sum of the angles must be equal to 180 degrees. So in the upper, which angles we have on the upper side of AB at point O? We have this angle that is a right angle, is equals to 90 degrees, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees. So 90 degrees plus the missing angle, in total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 180 degrees in order to complete the sum of the angles on the upper side of AB at point O to 180 degrees. This angle must be also equal to 90 degrees. Okay? And because of the fact that angle EOB is the right angle, therefore the pink triangle EOB is a right angle. Therefore we can implement the Pythagoras theorem on the right pink triangle EOB. So I copy the right pink triangle in a new page and we'll implement in this right pink triangle the Pythagoras theorem. This is the right pink triangle EOB that I copied from the original drawing. We already found out that EO equals to the square root of 5 units, OB equals to the square root of 10 units. So we implement the Pythagoras theorem on the right triangle EOB. By PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle, and especially in this right triangle EOB. The square of the hypotenuse is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Again, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, EB squared equals to EO squared plus OB squared. So EB squared equals to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So EB squared equals to square root of 5 squared is 5 plus square root of 10 squared is 10. So in conclusion, we found out that EB squared equals to 5 plus 10, that is 15. We'll take a root of this equation and we found out that EB equals to the square root of 15 units. EB equals to the square root of 15 units, that is to say the hypotenuse EB of the right triangle EOB equals to the square root of 15 units. EB equals to the square root of 15 units. Our mission is to find out the length of chord CB, this chord. We've already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of chord CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction. We will complete this semicircle to a circle. This is the first step that we will do. So in the first step, we completed the semicircle to a circle. In the next step, we will extend side OE in both sides, in the upper side and in the lower side. We'll extend OE towards the upper side until it touches the circle at this point. And we will define the touching point of the extended line segment OE with the circle as point M. In the next step, we will extend EO towards the lower side by a straight line until it touches the circle at this point. We will define the touching point of the extended EO and the circle as point N. So here, point O is the center of the circle and the semicircle. Point N is a point on the circle itself. That is exactly the definition of a radius. That is to say, ON is the radius of this circle that is equal to the square root of 10 units. According to what we already found out, the radius of the circle and the semicircle is the same. And likewise, point O is the center of the circle. Point M is a point on the circle itself. Therefore, OM is the radius of the circle that is equal to square root of 10 units. We have already found out that OE is one side of square DEOF that is equal to square root of 5 units. What is the length of ME? It is very easy to see that the length of ME from the drawing, that ME equals to MO minus EO. Again, MO minus EO equals to ME. I'll write it down. ME, the length of line segment ME equals to MO, that is the radius of the circle and the semicircle, minus OE, that is actually the length of one side of square DEFO. EO. So ME equals to MO, that is the radius of the circle in the semicircle that is equal to the square root of 10 units, minus EO that is equal to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. And we already found out that NO equals to the square root of 10 units. What is the length of EN? The length of EN equals to EO plus ON. Again, EN, it is very easy to see that EN equals to EO plus ON. That is to say, EN equals to ON, that is square root of 10 units, plus EO, that is square root of 5 units. In conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. Okay? And ME equals to the square root of 10 units minus square root of 5 units. In the next step, I will present to you a new rule, and we will implement the new rule number 2 in our drawing. The new rule number 2, is true in any circle. So here I will draw a circle that could be any circle. So in any circle, this is rule number 2, in any circle, we've called AB, this is called AB, intersects with called CD, this is called CD, the red line. In the intersection point between those two chords is at point O, this point. So I write it down. In any circle, if chord AB intersects with chord CD, and the intersection point occurs or happens at point O. Point O is the intersection point between the two chords. Then the following equation will be true, that AO times OB equals to CO times OD. AO times OB equals to CO times OD. Again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So we copy this drawing in a new page without the other things here, and we'll implement rule number 2. These two chords that intersect with each other. So we have here our circle. We actually know that chord MN passes through the center of the circle. This is called MN. This is called MN. That intersects with chord CB. The intersection point is here at point E. So I write it down. In our original drawing, we know that chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Repeat again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. And we already found out that EB equals to the square root of 15 units. So we put the data inside the equation and we find out the missing line segment CE. ME, it is actually square root of 10 minus square root of 5 times EN, that is actually square root of 10 plus square root of 5 equals to CE, that is the missing line segment, times EB. EB equals to the square root of 15 units. We'll find the value of this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5 according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. According to this algebraic identity, in our specific expression, A equals to the square root of 10, B equals to the square root of 5, and we'll implement the algebraic identity in our specific expression. According to the algebraic identity, A plus B times A minus B equals to A squared minus B squared. That is to say, A squared is square root of 10 squared, that is 10, minus B squared. B equals to the square root of 5, therefore B squared equals to the square root of 5 squared. Square root of 5 squared is 5. In conclusion, we found out that A squared times A plus B times A minus B equals to A squared minus B squared, and A squared minus B squared equals to 10 minus 5. And here it is equals to CE, that is the missing line segment, times square root of 15 10 minus 5 is 5, equals to square root of 15 times CE. Here we will divide this equation by square root of 15 and we will get that CE, the length of the missing line segment CE, equals to 5 over square root of 15 units. So we actually found out that CE equals to 5 over square root of 15. We actually looking for the length of chord CB. It is very easy to see that from knowing that CB equals to CE plus EB. CB equals to CE plus EB. So write it down. The length of the chord that we are looking for, that is to say CB equals to CE plus EB. That is to say CB equals to CE. We just right now found out that CB equals to 5 over square root of 15 plus EB. We already found out that EB equals to the square root of 15. Actually, the answer to the question is that the length of chord CB, this chord equals to CE plus EB. That is to say it is equals to 5 over square root of 15 plus square root of 15. We'll simplify this expression by multiplying square root of 15 by square root of 15, and then we'll divide it by square root of 15. So we actually multiplied this expression square root of 15 by 1, so we change nothing. So CB equals to 5 over square root of 15, and then we'll multiply square root of 15 by square root of 15, and then we'll divide it by square root of 15. So CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. So in conclusion, we actually found out that CB, the chord that we are looking for, equals to 5 plus 15 is 20 over square root of 15. Here we will multiply this expression by square root of 15 and then we'll divide it by square root of 15 in order to eliminate the square root in the denominator. Okay, so CB equals to 20 over square root of 15. We'll multiply this expression by square root of 15 and then we divide it by square root of 15. We multiply it by 1, so we change nothing. So CB equals to 20 over square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide both the numerator and the denominator by 5, and we'll get that CB equals to 20 over 5 is 4, so in the numerator in total we have 4 times square root of 15 over 15 over 5 is 3. So in conclusion, we found out that the length of this chord called CB equals to either 4 times square root of 15 over 3, or in terms of numbers it is equal to 5.164 units. Repeat again, the length of chord CB, this chord CB equals to either 4 times square root of 15 over 3, or in terms of numbers it is equal to 5.164 units. Okay, in the next step I will summarize the lecture. Okay. In the original drawing, we had the semicircle, and we know that the center of this semicircle is at point O. Inside this semicircle, we have square DEOF, this square, and we know that the area of this square equals to 5 square units. Our mission is to find out the length of this chord called CB. So first of all, we know that all the angles inside the square are right angles, so those 4 angles, they are all right angles, they are equal to 90 degrees in their sizes. And we also know that the area of any square equals to the side, one side of the square squared. Okay, we know that the area of square DEFO equals to 5 square units, and the area of any square, and especially square DEFO, equals to one side times itself. Why? Because all the sides of the square are equal to each other. That is to say, the area of our square DEF equals to 5 square units, and it is equals to the side squared. We took a root out of this equation and we found out that one side of square DEF equals to the square root of 5 units. So all the sides of this square DEOF equals to square root of 5 units. Then we joined points D and O together by a straight line. By joining points D and O, we actually created here the green right triangle DFO. So I copied the green right triangle DFO here. We have already found out that DF equals to the square root of 5 units, FO also equals to the square root of 5 units. And our mission is to find out the length of the hypotenuse DO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle DFO is DO, therefore the square of the hypotenuse is DO square, and it is equal to the sum of the squares of the perpendiculars, that is to say, it is equals to DF square plus FO square. So, DO square equals to DF square. DF equals to the square root of 5. Therefore, DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5. Therefore, FO square equals to square root of 5 squared. So in conclusion, we found out that DO square equals to the square root of 5 square plus square root of 5 square. Square root of 5 square equals to 5. Therefore, DO square equals to 5 plus 5. 5 plus 5 is 10. So DO square equals to 10. We took a root out of this equation and found out that DO equals to the square root of 10 units. DO equals to the square root of 10 units. Here we found out that DO equals to the square root of 10 units. But what is actually DO? 97 DO starts from the center. It is the hypotenuse of the green triangle, of course, but in addition, you can see that DO starts from point O, that is the center of the semicircle, and ends at point D, that is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, DO is the radius of this semicircle. Therefore, the radius of this semicircle DO equals to square root of 10 units. Here, point O starts from the center of the circle and ends at point B, that is actually line segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. That is exactly the definition of a radius, that is to say OB is the radius of this semicircle, that is equal to square root of 10 units. Likewise, point O, if we relate to line segment OA or AO, it starts from point O, that is the center of the semicircle, and then at point A, that is the point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to square root of 10 units. Okay? Then, I presented to you rule number 1, and we implemented rule number 1 in our drawing. What is rule number 1? According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. If AB is a straight line, and we have here point K, and line segment KL, so if we focus on the upper side of the straight line AB at point K, here, according to rule number 1, this rule, the sum of the angles on the upper side of AB must be equal to 180 degrees. The upper side is one side, therefore the sum of the angles on the upper side of the straight line AB must be equal to 180 degrees. That is to say, the sum of those two angles must be equal to 180 degrees. Or this angle AKL plus this angle, that is angle LKB. In total, the sum of those two angles, AKL plus LKB, they must be equal to 180 degrees. The same thing is true if we relate to the lower side of the straight line AB. In the lower side, the sum of the angles must be equal to 180 degrees. This is to say, this angle must be equal also to 180 degrees. We can implement rule number 1 in our drawing, because in our drawing we have this is a semicircle. AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point O, in the upper side of AB at point O, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of AB? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees in order to complete the sum of the angles on the upper side of AB at point O to 180 degrees. The missing angle must be equal to 90 degrees. And because of the fact that the missing angle EOB equals to 90 degrees, therefore the pink triangle EOB is a right triangle. Therefore we can implement the Pythagoras theorem on the pink right triangle EOB. So I copy triangle EOB in a new page, and we implemented the Pythagoras theorem on this right triangle, right pink triangle EOB. This is actually the pink right triangle EOB. We have already found out that EO equals to the square root of 5 units. OB, that is actually also the radius of the semicircle, it is equals to the square root of 10 units. The only missing side is the hypotenuse EB. So we implemented the Pythagoras theorem in this right triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Okay, so according to the Pythagoras theorem, EB squared equals to EO squared plus OB squared. So EB squared, that is the square of the hypotenuse, equals to the EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared plus square root of 10 squared. So EB squared equals to the square root of 5 squared, that is 5, plus square root of 10 squared, that is 10. In conclusion, we found out that EB squared equals to 5 plus 10, that is 15. EB squared equals to 15. We took a root of this equation and we found out that EB equals to the square root of 15 units. So here, EB, the potential EB equals to the square root of 15 units. Our mission is to find out the length of chord CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find is to find out the length of line segment CE. In order to find out the length of line segment CE, we completed this semicircle to a circle. Okay, then we extended side OE on both sides. We extended side OE in the upper side by a straight line until it touches the circle at point M. Point M is the touching point of the extended OE in the circle. Then we extended EO by a straight line until it touches the circle at point N. Point N is the touching point of the extended EO in the circle. So what is ON? Point O is the center of the circle, point N is the point on the circle itself. That is exactly the definition of a radius. That is to say, ON is the radius of this circle that is equal to square root of 10 units. Why? Because the radius of the semicircle and the radius of the circle, they are the same. Okay? So we found out that ON, that is the radius of the circle, equals to the square root of 10 units. Then, what is the length of ME? It is very easy to see from the drawing that ME equals to MO minus EO. Again, MO minus EO equals to ME. Here, ME equals to MO minus EO. Point O is the center of the circle, point M is the point on the circle itself, therefore ON is the radius of the circle that is equal to square root of 10 units. We have already found out that EO, that is one side of square, DEOF equals to square root of 5 units. Therefore ME that is equal to MO minus EO equals to MO. It is the radius of the circle that is equal to square root of 10 units minus EO, it is equal to square root of 5 units. In conclusion, we found out that ME equals to square root of 10 minus square root of 5 units. We have already found out that ON equals to square root of 10 units. And we also found out that EB equals to square root of 15 units. In the next step, I presented to you rule number 2 and we implemented rule number 2 in our drawing. Okay. According to rule number 2 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O is the intersection point between the two chords. Again, chord AB intersects with chord CD at point O. Then we can, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We actually can implement rule number 2 in our drawing. Why? Because in our drawing, we have chord MN that intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. Again, I copied the two chords with the circle in this new page. And we implemented rule number 2 in this following. According to rule number 2, because of the fact that chord MN intersects with chord CB at point E, we get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. En equals to the square root of 10 plus square root of 5. And finally, EB equals to the square root of 15. The only missing line segment is line segment CE. So we put the data inside the equation, in this equation that is according to rule number 2. ME equals to the square root of 10 minus square root of 5. NE equals to the square root of 10 minus square root of 5. CE is the missing line segment. And EB equals to the square root of 15 units. So here we have a square root of 10 plus square root of 5 times square root of 10 minus square root of 5. We found the value of this expression according to the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to the square root of 10 units, B equals to the square root of 5 units. So, according to this algebraic identity, A plus B times A minus B equals to A squared minus B squared. That is to say, the value of this expression, according to this algebraic identity, equals to A squared minus B squared. In our specific expression, A equals to the square root of 10 units and B equals to the square root of 5. Therefore, this expression equals to A squared minus B squared. That is to say, A squared is square root of 10 squared, that is 10, minus B squared. B squared is minus square root of 5 squared, that is actually 5. So in conclusion, we found out that A squared minus B squared in our specific expression equals to 10 minus 5. And 10 minus 5, according to this equation, 10 minus 5 equals to CE times square root of 15. 10 minus 5 is 5, so in conclusion we found out that 10 minus 5, that is 5, equals to CE times square root of 15. Then we divided this equation by square root of 15. In this way we found out the value of CE, that is the missing line segment. So we found out that CE equals to 5 over square root of 15. Okay, so actually we are looking for this question. We want to find out the length of this chord called CB. From the drawing, it is very easy to see that CB equals to CE plus EB. Again, CB equals to CE plus EB. Okay. Again, CB equals to CE plus EB. Okay. We have already found out that CE equals to 5 over square root of 15. We know that EB equals to square root of 15. So in conclusion, the answer to our question is that the length of this chord called CB equals to 5 over square root of 15 plus square root of 15. Here we simplify this expression. Why? Because we want to eliminate the square root of 15 in the denominator here. We actually multiplied square root of 15 by square root of 15, and then we divided by square root of 15. So we actually multiplied square root of 15 by 1, so we changed nothing. So here CB equals to 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. So in the numerator we have 5 plus square root of 15 times square root of 15 is 15. In the denominator we have square root of 15. Here 5, in the numerator we have 5 plus 5, that is 20. In the denominator we have square root of 15. So in conclusion we found out that CB equals to 20 over square root of 15. Here we multiply this expression by square root of 15 and then we divide it by square root of 15 in order to eliminate the square root in the denominator here. So CB equals to 20 over square root of 15, then we multiply it by square root of 15 and then we divide it by square root of 15, so we change nothing. So CB equals to 20 times square root of 15. This is what we have in the numerator. In the denominator we have square root of 15 times square root of 15 is 15. Okay? Here we divided both the numerator and the denominator of this expression by 5. Here 20 over 5 is 4. So in the numerator we have 4 times square root of 15. And then we divided the denominator 15 by 5. 15 over 5 is 3. So in conclusion, we found out that CB equals to either 5 times square root of 15 over 3, or in terms of numbers, it is equals to 5.164 units. I'll repeat again. We actually found out that the length of this chord called CB equals to either 4 times square root of 15 over 3 units, or in terms of numbers, this line segment CB equals to 5.164 units. Okay, thank you very much.